So the details, I suppose that I won't stay with this map again, okay? Because this is a wrong diagram. Okay, so what is wrong about it is this based on something we mix it up. Suppose you print an address in your program. This is not something we call physical, but virtual. Okay, every time you print an address, it's a virtual address. So that's why the previous, no, this one. This example, when you see this address, it's actually the virtual address. And very interestingly, this kind of addresses together with the instructions. There are address in the instructions, right? They are all coded in terms of virtual address, not physical address. Okay? So that means that whatever the CPU want to work with addresses, whenever you want to load an address from based on a program counter, no matter it is inside the instruction itself, why is it possible that inside the instruction there is an address? It is usually a practice by the compiler. The compiler wants to code an address there. And they don't code any physical address. They are all virtual address. And every time when you do a thing like loading address, loading instruction, executing instruction, all work on the virtual world. Okay? So whenever you want to find that particular data from the memory, then this is the time that you ask the MMU to do the translation. This is the only time. You want that piece of memory, okay? I want to load that address. The program counter says this address. I want to load it now. You will go through the MMU to translate your address in the virtual world to the real world. Okay? So this is translation happen whenever you want something or you want to write to the memory. Okay? So here is the diagram. And last time I stopped at this page. Okay, so this just an animation. Let's stop at this page. This page, I missed one very important explanation. The explanation here is we have two processes, right? I said that they code everything, run everything in the virtual world, so they don't know there is another guy using my same address. Okay, so this is a very important concept that I didn't mention. That's why you see the virtual address inside both processes may be the same. Okay? They may know the same set of addresses, and they believe that that address will guide you to a piece of memory. Okay? And of course, because they are of different processes, they will be mapped into the real world, but different addresses. Okay? In this example, this different address. And this particular method of mapping from virtual world to the physical world, actually enable one more feature. Okay, so this is the feature very straightforward. Okay, this guy has a variable, let's say, stored in this address called 1234578. This is a memory address. I want to store something there. Of course, I want to map it into two different area or two different memory, so that I can save different things on different processes, and they won't pollute each other. Okay, so this is very important. And other even more interesting stuff is the next step. The next step is here. So what this guy is doing, you can see this, the virtual world, see the same address. When the CPU translates it, these two processes map to the same physical address. So what does it mean? This means memory sharing. Yeah. This is how we enable memory sharing. So imagine that there is a special fork call. Let's say the fork call, after you do a fork, the two memory won't separate it, but share. That will be this that case, right? You all actually do this, okay? And allow two processes to share things. And also allow the different processes to map to different area during the fork. During the fork, let's say this is process X, this is process Y. When you do a fork, everything will be duplicated within this virtual world. But when you map to the physical world, I copy a new area for you, map it into another address. Okay? So this is how the computer can set up fault call, how to duplicate the memory, how, let's say, the fault call is so special that allows you to share something. This is it. Okay, this is the way. Okay, and it seems that the MMU is so clever, right? How clever it is? The MMU is just a little CPU-like thing alongside the CPU. Know which process you are. Okay, whenever you are from process X, I map to a particular address, let's say X. Here, if you're from process Y, I map to area here is Y. Now, how is this possible? Now, let's take a look at the time that we only have one process, so as to kickstart the entire discussion. Okay? So if you have any questions and any thing that you don't understand, stop me immediately, because it's kind of related to a hardware thing. Maybe it's kind of a never seen before. Okay? So you stop me, I will try to explain to you. Okay, so this implementation, and it brings about a new term called paging. Okay, so maybe you have heard of this name. Something tell you this. Oh, there's a thing called page table, page size, whatever, page faults. Okay, so maybe you have heard of this guy. That page is this name. It's called paging. It's a technique. Okay, later on I will go through the technique with you, and all things happen within the MMU. Okay, so what is the MMU? MMU is just a mapping function. Yeah, as I said before. Let's say, imagine that we start with the number one naive implementation. What is the naive implementation? It's just a lookup table. Okay, and we restrict our implementation to 32-bit CPU only. Okay, so to make the discussion easier. Okay, so what is the mapping now? I know that the entire process know that there is a virtual world from the 0 address to X0x8F. Okay, so 32-bit. And now I tell you that actually that is a false claim. Okay, we should not claim that all memory belongs to you, but you will map to some physical address area. So you have to write another set of data for the CPU to map, right? Just like this. And actually, this mapping is very easy to calculate. What's the size? The size is not here plus here. This is only an index, okay? But there's an index. Oh, index array index 0, array index 1 up to array index 0x8f. Okay? So you don't have to worry about the left-hand side. Now, our right-hand side, you need space, right? You have to store that. Oh, I know that when you present 0 to me, actually 0 won't map. Okay, 0 is a null pointer, right? Let's imagine it will map. Okay, it maps to this address. Okay, and I'll do another mapping, and the mapping is based on every bytes. Every byte is mapped to another location. Every byte mapped to another location. Now, what is the implementation of this? This is a naive approach. Okay, and the naive approach is too naive that no one has implemented. Why? That's the calculation. The calculation is this area is going to be safe. Every mapping will map to a 4-byte entry, right? One element is 4 byte. Now let's say that I will map the entire address space. Address space for here is a 2 to the power 32 entries, and every entry is actually this 2 to the power 32 entry. Each entry go to a real address, so this is 4 byte, and we limit it to 32-bit, so that this is easier to calculate, and it is 16G. Okay, you don't expect that in your CPU there is a 16G lookup table, right? If yes, then good. We don't need any CPU because it never exists. Okay, so this is not the real implementation, and the real implementation they make some trade-off. Okay. And the trade-off starts with this calculation. Okay, so this calculation is very important. This calculation is telling you that mapping byte by byte sucks. Okay, I map every byte to another byte, then we need 16G. Now, how about we have a granularity like I map several block and address to another block. And what is the meaning of it? I have a diagram. Okay. And the diagram later on, I will need my drawing pad to draw it again. So what is this diagram? This diagram is close to what we have inside MMU. Okay, so the MMU is doing something like this. There is a smaller lookup table here. We call it a page table actually. Okay, we have page table, a smaller lookup table, and this smaller lookup table will transform not all 32 bits, but part of it. Part of it. We can choose. But nowadays technology is we only map the most significant 20 bits. Okay, most significant 20 bits. So I will do this mapping. You give me a virtual address, so I chop it off by 2 halves. One half is the most significant 20 bits, and another half is the least significant 12 bits. Least significant 12 bits means the smaller values, right? This smaller value won't change. So I'll do a copy and paste here when I do the mapping inside MMU. So do a copy here from here to here. Then here, it's not a copy. It's the real mapping, real change. Okay? So this is going to be a smaller lookup table, right? I think you agree. Because the number of possibilities here is no longer so many bytes, right? Not 2 to the power 32. It's reduced to 2 to the power 20. Number variety, okay? And now I do this mapping, I reduce the memory to 4 megabytes only. Yeah, seems to be attractive, right? But of course there will be a trade-off, right? I want to map a byte. Now you are not telling me that I'm mapping a byte. What is the data I'm mapping? Okay, so very interesting. We do this translation, actually we don't know what is the mapping results. I don't change this, but keep on changing this. Now I have an illustration what this whole mapping means. If it makes sense, then the calculation is good. If it doesn't make any sense, so why we have this calculation meaningful? No, right? If it doesn't make sense. Now, let's see how it means. Okay? This is just words. I will come back later. Okay? So what is the meaning? The meaning is I use this continuous virtual address area to explain to you. Okay? So what is this continuous? You can look at it here. It has a decimal value. 1, 2, 3, 4, 5, and then 0, 0, 0, right? And the next will be 1, 2, 3, 4, 5, 0, 0, 1, and keep on increasing, and then we will eventually go to 1, 2, 3, 4, 5, FFF. Okay? Now, what is the next address? Next address is now FFF. I have add one more, it will become 1, 2, 3, 4, 6, and then 0, 0, 0. Okay? And so on and so forth. Now, why I highlight this area? Okay? Because this area contributes to how many bits? This area. If it is a 32-bit address, 3 guys here. Each guy's how many bits? 4. Then 3 will be 12 bits. Okay? So this area actually 12 bits match what? Match this translation. This translation say that I won't change the least significant 12 bits. Okay? So I just write here, so highlight here, the 12 bits untouched, don't touch it, keep it here. And what we are going to translate is from this virtual address, I chop it off into half. I will change this 1, 2, 3, 4, 5 guys. Okay, the 5, you can call it digits, okay, but yeah, just you want to call it digits and digits, okay. So I will change this 5 guys, and this 5 guys, how I change this? It's very interesting. No matter how this least 12 bits changes, okay, no matter how it's changed, it will be copied, right? It will be copied to this physical address, no matter how, right? Because I say that I won't change this guy, so I'll copy it one by one. Now, what this means that whenever I see 1, 2, 3, 4, 5, please look up into the lookup table, right? There's a lookup table here, it's called a page table. I will try to match this into an order guy. Let's say it's called 5, 4, 3, 2, 1. Yeah. The translation is reversed, okay? Yeah, 5, 4, 3, 2, 1. Now, every time I do this, every address will supply to me, I'm doing that. So you will end up with this layout. This area won't change, this area won't change. Only this area change, but every 1024 address is it 124? Oh, no, 4K, okay? Every 4K address, why is 4K? 2 to the power 12. 2 to the power 12 is 4 times 2 to the power 10, so it is 4K. Every 4K addresses, I map it to another 4K address continuously. Okay? Understand this? I do this translation just because every prefix here will do this change. And what is the end result? The end result, if I do this mapping, you are changing a block of 4K into another block of 4K. And nowadays, 4K is our what we call a page size. Okay? This is what we call a memory page. Okay? This is a memory page. Every time you give me an address, okay, I will know which page it should be, okay, and his neighbors, his brother, sister, okay, this guy, let's say you find me this address, his brother and sisters, or the whole family of 4K addresses will map to the same block. How about the next guy? The next guy is here, this guy. Because this guy, what we call this, we have a name. The name is called the virtual page address. No matter what, okay? No matter how big it is, okay? Let's say it's November 20 by 24, okay? We still call it virtual page address. Now this virtual page address change from 12345 to 12346. Then the whole page will map to another area. Okay? So what's the end result? The end result is a process now become from a virtual address continuously allocated given to you in a memory is scattered. Scattered whole around the entire memory, and the memory is dissected into each chunk of 4K memory block. We call it page. So a memory actually become an array. Okay, memory originally is we think oh it's byte by byte. Now it's page by page access. And I can give you a drawing here first. Drawing, where are you? Yeah? I deleted drawing. Oh, sorry, I deleted drawing. Maybe later I draw it. Here. Okay. So you have this virtual page address mapped to some scattered area, some scattered around. Okay. So let me go back. Okay. So here is just a simple illustration. It's been scattered, no longer continuous. You give me a virtual address while you're going inside the CPU to execute, I map it to that page. Okay? And actually page address you can find even when you buy a CPU. Okay, let's say what we want to look up, maybe Intel Core i7. Okay, when you look up its specification, it will tell you what is its page size. Okay, let's see, page. Hey, come on, page size. Okay, maybe this, or maybe we look up some images. Images may be easier. But thank you. Oh, okay. I found something interesting. Let me see. You may not be able to see it. Let me see it. No, it don't say anything about a page. Maybe take a look here. You see it? Page. So wow, what's that? VTX extended page table. Crazy. Only one? Okay, thank you. Yeah, Intel sucks. Okay, Core i7 page size. Okay, wow. Let me see, is there any images? No. Here. Let me see whether this have hey, come on, no faster. Wow, can you see whether I've got I'm stupid. Okay. Can you see the page size here? Page L1 cache. I can see a price. Oh, no page, they chop it off. Okay. Maybe I search for another keywords. i7 big page size. Wow. Okay. I is find all the new measurement. Okay. Maybe later on I find out and post it up here. Post it in Facebook. Okay. I find that there is some specification talk about its page size and what are the variety of the pages that a new type of Core i7 support. Actually, Core i7 allows you to support not just 4K page, a bigger page, okay? Depends on your choice, okay? Now, this is the basics of what is paging. And what is the motivation? Yeah, maybe you lost the motivation, right? The motivation is, I don't want to look up things by, because I am building up a huge lookup table, which is forbiddable size 16G lookup table. No, okay? I prefer something small, which can be fit in the CPU, okay? And for my calculations, actually, because it's a 32-bit CPU, every computation based on a 4 byte size area, but the number of translation entries now become 2 to the power 20. So it's only 4 megabytes based on my previous illustration. Now, whether this is the truth or not, no, this is not the truth. But this is easier for you to understand. Okay, if you want to know more, I know that we don't have enough time, so I cut this out. If you want to know more, look up this keyword in Google. Yeah, you already know how to understand that. TLB, page table. Okay, so this is the real implementation. We call it translation lookup site buffer. A tree-like allocation style, not an array lookup table, but build it as a tree. Okay, and there is a tree hiding in our CPU. Okay, so if you want to know, okay, you can ask me for the notes. Okay, I already prepared it. Maybe I also pull it up. Okay, there's a tree lookup table called TLB, which is the real implementation. Okay, and this is just an illustration for you to understand. Yeah, this is nowadays how we do this. Okay, and this just works. Okay, and actually we don't call it lookup table anymore. We call it page table. And every process has its own page table. Why? Because I am process A, I know how to map. You are process B, your mapping is none of my business, right? So every process will have its page table. So what is the ending result? The ending result is context switching. You need to switch the page table. Whenever you switch from one process to another, the page table switch as well. Okay? Yeah, very tedious. Okay. So yeah, this is the illustration. What is the page size? Page size Y is 4K. Okay, and I already talked about it. Now let's go to something coding. Yeah, something that you will now know what is going on. Okay. So what is this program? This program is a very interesting program. This program actually worth your, maybe if you have a laptop, you can always start your laptop and try this program out. This program may take you 5 minutes in order to understand what is the purpose. I will go through it line by line with you. First of all, the highlight here. The highlight here is the code that I last time in the last part talking about a heap. I mentioned it's called break. Okay, its system call is called break. It's an S break is its brother. Allows you to grow or change by increments. You can have a 1 means add 1, minus 1 means decrement by 1. Okay, and that means that what I'm going to do, I start with a clean program, clean process. Okay, no malloc. Okay, I never touch any code that may call malloc as well. And what I'm going to do, I will want to grow that allocation by 1 byte. I want to grow that by 1 byte. And one more call, sbreak 0. Sbreak 0 means I read the current heap location. Okay, which is doable. Okay, not location, that's the highest point. Okay, I say the highest point. Okay, so the heap start, I get it. Now I increment by 1 byte. And what I'm going to do, I want to walk, increase, right? Walk upwards, okay? Now what I'm going to try is actually, I don't believe when you do this SBRK1, you get 1 byte only. Okay? What I want to propose to you is something that you already see, right? You comment on, okay? Everybody will say this, no problem, let's just let it go off bound. And what is that bound actually? It's 4K. This will try to walk upwards, okay? And when it stops, exactly 4K bytes. That's right. Yeah, very crazy program, I know. Okay, why is ESPN here? Why I touch CSCI, what happened? Okay, touch page size. The same program, okay? So I run it on Linux so that it is not depending on the Mac OS anymore. Okay, so I will also measure the pointer changes by monitoring its stored using a previous pointer, and then here the calculation is based on the position that I generate the segmentation points minus the start. Let's go. 4K. I grow the heap by 1 byte. Actually, I give 4K. Why? It seems to be related to the page table, right? Actually, this is not a secret, okay? Everyone have taken an OS course should know about this. Whenever the system want to allocate space to you, how can they allocate the space to you? By what? By adding an entry in the page table, so that your virtual page address can map to a physical page address. Right. This is the must. Okay. If I don't add that translation, you cannot translate it, and you will have some problem. Now I want to let you translate it, so I give you that entry, but I cannot avoid giving you the whole page. Right? I give you one address, but I cannot avoid the remaining. Once I map one virtual address to a physical address, actually I'm giving you a whole page. And that whole page cannot be shared by another process. Right? Take a look back. Yeah, this is going to be hard, okay? Take a look back here. I give you one address. Let's say this is the beginning of your heap address. I give you this address. I say that this address will map to this physical address, which is a piece of real memory. Can I avoid giving you the remaining? You may say yes, but can I share this remaining area to another process? No, I cannot. I cannot share it because this physical page is actually belong to you. I give it to you. Okay, give it to you by adding you this entry in your page table, so that the basic of allocation now, you understand, when you try to allocate something which is smaller than one page, you will get one page. Now try something more. How about this? Yeah, this is gonna be tougher. How about I grow not 1 byte, 1,000 byte? How about this? Okay. So I say that heap go up by 1,000 bytes. Still, it is one page. Still one page. Oh, sorry. Yeah, then I know what you want to try. Huh? 5,000. What is 4K? 4K is 4096. Now I grow the heap by 5,000 bytes, more than one page. So what will you get? Two page. Okay? Yeah, quite not interesting, but quite hard to understand, right? It seems that now the CPU, because of the paging mechanism, I give you a new address, translation, become valid now. I'm forced to give you that and you're entitled to the whole page. Okay? And that whole page now goes to you. That's why whenever you have a problem in your malloc call, it seems that you cannot really believe in your natural sense that yeah, don't go outside the bound, because there is a 4K buffer for you to grow. Okay, it's actually the mechanism because of the nowadays CPU design. Okay, and let's say if you grow 1 byte and this program tells you 8192, that means that that computer change. 1 page is not enough. Maybe it allocate 2 pages to you, or even it change the page size. Or it seldom happen. Okay, I say never happen. It should be. Okay, so then based on this program, actually I do a little experiment. The experiment is like this. I make different requests. Okay, request, let's say I do it every time. I remember it's a 512 byte increment. 512 byte increment, 512 byte increment. Okay, so you will see that based on this program, the allocation is a step-like function, right? You go beyond that 4096 boundary, then you will get 1 more page. Go beyond that boundary, you get 1 more page. Okay, so every time you get page. Now, this is kind of crazy, right? More crazy stuff is this allocation, okay, not just happen inside your heap area, it also happen in stack, also happen in global variable. Let's say you say that you want to have a global variable which is 1000 byte, actually you got 1 page. Okay? So any question you want to ask? Yeah, this is kind of difficult, right? Because it's the first time you heard of that. Actually, it's like that. Yeah, but when you know about it, then you get a sense that actually you know the behind working there is actually giving you more memory because of this. Yes?
Is this the reason for internal fragmentation?
Yeah, I can hear you.
Is this the reason for internal fragmentation?
Yeah, there is an internal fragmentation problem. Sure. Because that page belongs to your process, cannot share to another process. Yes? Any problem? Any question you want me to clarify? Yeah. Okay? Yeah, this is quite important stuff. Okay. Yeah, this is an internal fragmentation problem, okay, that you have mentioned, okay? So when I increment it, actually that whole page belongs to you. And then we will end up with something like this. What is it? Okay? You are going to grow your memory. Whenever you want to grow your memory, a new page is given to you. A new page is given to you in the sense that with different colors, right? Now it's become every 4K trunk, and it's scattered inside the memory. I don't know where it is actually. Only the page table know where it is. Okay? And one more stuff is this every 4K guys, okay, every guys now is 4K, may have a chance to go into the hard disk. And its basic transfer units is also 1 page. Okay? So that means that this E guy, this 4K size, it may inside the hard disk. Depends on the allocation inside the memory. Now you may understand that the memory now has become an array. Every element is 4K size, 4K width. Every element is there, and every slot may belongs to may belongs to different process. Every slot may belong to different process because this whole piece of memory is going to be shared based on your page table. Okay, your page table say that okay, I allocate 1, 2, 3, 4, 5, and your page table say that okay, I allocate 9, 6, 7, 9, 6, 7, 8. Okay. Now what happens here? This guy sucks. Okay, and now we have the next wave of questions. Okay, why it go to here? How it go to here? Okay, why, how, when? I wish to put this topic in later part. Okay, because it's going to be a very boring. Wow, what's that? What's that? What's that? Okay. So maybe I don't stop here. I will come back to talk about this next lecture. Okay. I will give you one more concept. This concept is easier to digest because demand paging. Okay, and the demand paging is actually the solution to explain my real OOM program. But remember my real OOM program? My real OOM program doesn't really get the memory until what? Until I really do the MEM set. I use the memory. Okay? Now, what this means? Okay, so let's imagine a scenario. Or maybe I show you the program is better. Okay, so what this program is doing? Crazy stuff. I have a buffer. I have a buffer inside the function, just like previous times. Remember, my previous stuff has a buffer inside a function. I call recursion. Ask it to grow. Okay. Now I will explain to you some feature of a top program. Okay, first, top program. Okay, maybe I quit it now. So what is this columns? Last time I tell you these 3 columns is responsible for the memory part. Okay, now I can explain to you what this 3 guys is. This first guy is because virtual memory allocation. Your virtual memory knows that you have so many pages or so many memory. And here, we call it resident memory in the physical memory. It means this virtual address now is being used. I give you this virtual address, so I give you that page. If that happens, it will go to here. I give you that page, then it will go to this column. And with this column is using the page table sharing technique. I use 2 different page table, but 2 different page table point to the same physical page. Okay, and there's a sharing. Okay, so these 3 guys, I won't explain or I won't tell you how to do the sharing part, but I want to demonstrate these 2 guys. Okay, so what is the difference between the virtual and the resident memory? I have this program. Maybe I need to spawn one more terminal. Wait for a moment. Yeah, no. I'm not on this VPN. Okay. Good. Come on. I have to be very careful, huh? Last time I leaked my password, okay? I have to be very careful. Okay, so let me start the program first. It's called grow stack. Okay, so the PID is this guy. PID is this guy. So I will make it bigger. Top minus P. This guy. Good. Okay. So this is enough for you to see, right? I also minimize this guy. I don't mean to. Oh, very hard to control. Touchpad really sucks. Okay. So what I'm going to show you, I show you how these 2 columns change based on what I'm doing. Okay. So let's take a look at the program first. The program, is now the growth based on the paging, right? Whenever I open up a new stack space by calling recursion, that means that I need that virtual address. So I will grow my virtual address consumption, but whether that virtual address consumption will map to a physical page, that's the question. So I will have this allocation of the virtual address first, but this doesn't really mean a physical memory allocation. That means whether the page table will help you to map the physical page. And this is the moment that we will have that mapping. So this is the moment that I stop in the program. I stop in this area, the line 4. Then when I press enter, I will make the real page consumption. Ask the CPU that, hey, I want to touch that address now, okay? Please really prepare a page for me. Then another enter, then we'll loop back, because of recursion, right? Not loop back, okay. One more function. One more function to grow my virtual address consumption, but it doesn't mean I really consume that physical page. So what we will see is like this. Very, very crazy, okay? Take a close look to these two columns. Now, it will be growing resident memory. Press one more enter, I will grow the virtual. One more enter, resident. Virtual. Resident. Virtual. Resident. So I said it's called resident, real allocation. Okay? So there's a magic here, right? What happened? I asked for that virtual address. I have those virtual address now because I say that the program function called grow array, it doesn't mean a real allocation. And that technique, we call it demand paging, I have a better name, lazy allocation, really lazy, right? Claim that you will do something just like you tell your mom, yeah, I will do it, okay? Actually, you're not doing until he or she, not he, okay? She, okay? Until she go to check, okay? When did you do it? Okay, then you will do it, right? It's lazy allocation, demand paging, or murder allocation. Yeah, yeah, just like this. Yeah, will now virtual will, okay? And this is the beginning. And how it is implemented inside the CPU, I will go back a few page slides next time to explain to you why this is going to happen. And we will end this part, not tomorrow, in the coming Thursday, by one very extraordinary illustration. I won't illustrate it in my computer. I will bring my EPC. To explain to you what really happened inside OOM. Yeah, what is real allocation, what is virtual allocation, why add up together, I will consume all my memory. Okay? Good. So next time, remember, we will resume the talk based on this page table design, how the page table design helps you to come forward the implementation of the demand paging. Okay? So, yeah, this is hard, huh?